We are going to look at determining whether series are convergent or divergent by looking at integrals. So first let's consider this series, the sum of terms 1 through infinity of 1 over n squared. And let's look and see if we can figure out if that converges or diverges by looking at its behavior. So if we start listing out terms, we get 1 plus 1/2 plus 1, oh, not 1/2. 2 squared is 4. And then 3 squared is 9. And then 5 squared is 25, etc. Okay. And then let's look and see what that would look like on our graph of 1 over x squared. If we were to graph that function, what we can do is we can create a Riemann sum that has these terms as its individual term of the sums. So we're going to create rectangles of length 1 with a height of these values. So with the height of 1, width of 1, that's our first rectangle. That area's rectangle is 1. If we go to n or x equals 2 and create a rectangle from that, the width is 1 and the height is 1/4, because if you plug 2 in for x, you get 1 over 2 squared, which is 1/4. And if we create another rectangle over here, that would be 1/9. And another rectangle, that would be 1/16, and so on and so forth. So if you look here, we can say that the area under the curve from 1 on, this area is going to be bigger than the sum of these rectangles, right? Because the rectangles don't cover these little pieces that the whole area will count in its sum as well. So we can say that if we, in our sequence, we can have 1 plus our series starting at the second term. Okay, that would be adding this rectangle and all the rectangles on the right side, which are really just the first term plus the sequence or the series from its second term. So starting at 1/4, that's from here over. That, because it's underneath the curve, is going to be smaller than this 1. Oops. Plus the integral, or the area under the curve from 1 to infinity of 1 over x squared dx. So if we're looking at just this point on the series, those areas, when you add them together, are going to be smaller than the actual area under the curve, because again, because of those little bits that aren't counted in the rectangles. So if we know that the sequence is smaller than the area, and we can tell that the area converges or has a sum, and it's bigger, that means that this would also have to have a sum. Okay, so all we have to do is find this integral right there. So this is an improper integral because it has a bound at infinity. So we're going to take the limit as t approaches infinity from 1 to t. And then we integrate, so we get negative x to the negative 1, so it's negative 1 over x, evaluated from 1 to t, taking the limit as t approaches infinity. That'll give us the limit as t approaches infinity of, when we plug in t, we get negative 1 over t, minus what we get when we plug in 1, which is negative 1. And when we plug in infinity, or we think of t approaching infinity, like this getting larger and larger, this number is going to approach 0. And then minus -1 is +1. All right, so we have a finite area under this curve, +1, that's bigger than the second term up of the sequences plus its first term. So because this converges, the area converges, that means that the sequence also has to converge. All right, let's look at the actual rule based on that idea. So the actual integral test, given f of x is a positive, continuous, and decreasing function on a closed k to an open infinite interval, if the integral of f is convergent, then the sequence is also convergent. If the integral is divergent, then the series, these are series, then the series is also divergent. And we could prove divergent series as well by doing the same thing, like drawing a curve, and instead of drawing the rectangles under the curve, you would draw the rectangles over the curve. That would make the function bigger than the sequence, and if the function is bigger and is divergent, then the series is also divergent. So you can draw those either way, and that just will tell you, based on what the integral is, the series will follow the same suit. So we're going to use that integral test to decide whether this is divergent or convergent. So all you have to do is take the integral from 1 to infinity of 1 over x dx. And that's an improper integral again. So 1 to t. And let's see, that will give us, that's the limit as t approaches infinity of ln absolute value of x evaluated from 1 to t. And that'll be, oops, if I undo that, there we go. The limit as t approaches infinity of ln absolute value of t minus ln of 1. Alright, so if you look at t approaching infinity, when t gets larger and larger and larger, the ln of that larger and larger value is also going to get larger and larger and larger. Ln of 0 is just 1. So this is going to diverge. So because the integral diverged, or there's no finite sum, that means the series also diverges. Okay, and we've just done 2 examples of p-series, and there's a specific rule for p-series that we can use. You can use the p-series test. The series 1 over n to the p is called a p-series. It converges if the exponent p is greater than 1. It diverges if it's less than or equal to 1. Alright, let's look at one more example. Okay, so we are given this series and we want to determine whether it's convergent or divergent. So I guess it's important to note that you can only use the integral test when the series is positive, continuous, and decreasing. So if we would like to check those, starting at term 1, or when we plug in 1 for n, that's going to give us a positive value, and anything higher than 1, like if we plug in 2, 3, 4, 5, those are all going to be positive. So this is a positive series, or it's going to give us positive terms. It's continuous, as in there's no discontinuities. We're not going to get anything undefined, and we can check that by looking at the bottom. When the bottom is 0, that makes it discontinuous, but we are never going to have it equal to 0 because n starts at 1. So this would be continuous. And decreasing. So what you want to do is you want to look and see, is this going to get smaller or bigger as n gets larger? So as n gets larger, the bottom is going to grow faster than the top, so these values are going to be getting smaller. So this is decreasing. So we could go ahead and use the integral test. So we will take the integral from 1 to infinity of the square root of x plus 4 over x squared dx. That's an improper integral, so we're going to take the limit as t approaches infinity of the integral from 1 to t, square root of x plus 4 over x squared dx. Alright, so what I would do with that one, we're going to kind of look at all the different tools we've learned to integrate. On this one, I would just split up the numerator. So let's rewrite that as square root of x over x squared is 1 over x to the 3/2, or you could just write it as x to the negative 3/2. And then 4 over x squared, that's 4 times x to the negative 2. And we can go ahead and integrate that. Oops. Okay, the integral of x to the negative 3/2 is x. You add 1, divide by the new exponent, so that's x to the negative 1/2 divided by negative 1/2. And then for x negative 2, we add an exponent, so negative 1 divided by the new exponent, negative 1. And we're evaluating that from 1 to t. That's a t over there. Let's write that a little nicer. Okay, and again I'm going to rewrite that, putting the exponents on the bottom. Okay, and then we evaluate by plugging t and 1 in. Okay, now let's evaluate the limit. So as t approaches infinity, for both of these first two terms, as the bottom gets larger and larger and larger, the tops get smaller. So that's going to be 0 and 0. And over there, those are just numbers that don't diverge. So that'll give us plus 2 and plus 4, so 6. Okay, so our integral came to 6, or it converged. Since the integral converged, that means that the series must also converge. So the series converges or is convergent.